you hear back?
I sent the email to you.
Yeah, I saw that.
So it may be up to you.
Okay, well, I can send you an email back, but let's go ahead and put her back in.
I mean, she's still in course. I see go in and make her active speaker.
Okay, so you'll do that, then I'll raise that one. For it.
Then call Rachel.
Yeah.
And then I'll go in. Okay. Let me do it right now because I have to leave campus right now.
Okay. If you'll do that.
She's the only one you have.
It was 111 concept.
I'll go with it and reactivate her and do this little apply all and let everybody know that she's going to stay in the forms.
Okay.
See, I can't see the day of release. Again, why have you
Technology is wonderful when it works.
Yes, it is.
There's my dry erase markers. They names are always
Very failed.
yeah, well, they do occasionally dry up, but I have a supply right across the hall. So, let's see. Pull this one. And then, that's not flash through. Put flash yellow blue, not solid blue. Amanda? Amanda, are you there?
I think it might be.
So far.
Okay, can you hear me now? Are you there?
Yes, I'm
Yeah,
here.
we're
I'm
here.
just turning the fan down.
Okay. So I am just taking up their partial credit, not the original test, right?
Correct. Just their,
Okay.
because I do have the originals here, so.
Okay. I laid some paper clips up here, guys, if you want to paper clip them instead of staple. You got it.
Might be a finish later on.
Wait a second, Chloe, I'm not done.
Oh, okay.
I'm sorry, another road.
Wait, the beast.
I solved it
Because
I
the
just
weeds
don't
here
know how
never
to write
came
it.
up to the area.
Okay. So how would I write it?
And then we got
like I simplified it that much.
And then
The absolute of 1 over x times the absolute value. The absolute value of 1 over x times the absolute value of 1 over
and then
x.
this is cool. That one
Wait,
with all the
why?
bands.
I guess you just do.
Okay. One.
What was the first
Wait, what?
Because it's x
it
squared, so
was
you
just
just do
the green
1 over
squares.
x times 1 over x, and that'll give you 1 over x
So I
squared.
put x.
Going to that number two, I think I'm on this.
Like I got all of
I
this
got it
right. I
for
just
free
don't know how to
because
put it
they
in this to where I end up with
Mom's just like, that's good. That means you're gonna have to spend $6 on you, and it's just.
I like it.
Did you get the graph?
Yes. Yes, I did get
and
the
then
graph.
that is
And some of it was so either I like barely missed
and
them,
that is
or I just did not think of how to actually do it properly at the time.
And so then your n is
Like number 6 with A and B, the find delta was so easy for me to actually redid it. It's
then the
basic math.
It's
It's basic math. I didn't think to do it algebraically before.
I did the first one, but I think.
why wouldn't that be
And there's like 2 or 3
Because you
columns I just
substituted this for n.
skipped over like a word or two because I was trying to rush through so I'd finish. Like on number 10, it had to satisfy like 2 criteria for the equation. I only read the first part, and to satisfy the second part, just had to add +1.
Yep.
like that?
It was the same exact.
So what am I concluding?
This
Whenever
one
x is located
Oh, I
in the
got it.
function interval, this gives us that.
I just did not write
Like
that
you
big of
just
an
take the
explanation
first two
this
and
time.
smush them together.
Okay, thank you.
I wrote a big one before though, so I felt obligated.
We only
I
had to
didn't-
do homework on this slide. Or one about my notes, I think.
Sorry.
I'm Chloe.
Yeah, just what I never heard that.
Like for the graph, when you have your x equals negative x minus 1 over x. So would that look like in the middle of the
Yeah.
and you can do a little box.
You don't have to, but it's really fun.
this is the later stuff in the chapter. This stuff is what. This stuff. Chemistry yet. That's for today.
Finishing 1.5 in class today.
Kind of thinking of leaving that.
Did we do the study?
If you're still gonna show me, it should kind of, if we missed a part of a problem, we would have to do both parts.
I don't think so.
No, but that's the logic that follows.
Okay, I only did the part that I missed, because in that case, I'd be redoing
I
every
still
single
wrote
problem.
it perfectly first time or whatever underneath.
I didn't even put that, I was just like, I got it, I'm out. Because in that case, it's not small pointing off on basically every time.
It's the what?
So in that case, I'd be redoing the entire test now.
No. It'll start getting really hot in here when it starts getting really cold outside. It's pretty much the opposite. Whatever the weather is outside, it's going to be exactly the opposite inside.
Because I was like, well, we still have to do
I'm sorry, say,
Say, yeah, we must be in the same school system, because it's hot in two places in here right
But I don't understand any of the
now. It's
difference.
it's outside. So it's time to get started, I guess. Something like that. Got works there, and let me check the roll real quick. Back, come on now. I wrote on the board main theorems that we've discussed, except for one that we haven't discussed yet. These are the main ones we use. So these ones you're really going to be familiar with. Razor is not here.
He'll probably slip in soon.
Parsons not here. Probably slipping a little bit. Dylan and Kyle are not here. Okay. Well, thank you. Pardon? Yeah, you do. Okay, so for homework you were asked to finish looking at section 5, and we're going to talk about this more today. That's what we do. Is look at problem 1 in section 5 for a few minutes, and then we'll pick up where we were last week. I asked for Drew over there, but I think tonight we'll pick up. Okay, so section 1.5 on page 134, problem. All those theorems that were on the board, they're in your book. I just wrote them up for you as kind of a quick summary of the key ones that we use. Well, okay. Alter line. Yes, Mason.
Okay. A. True or false? The limit of a difference of functions as x approaches c is equal to the difference of the limits of those functions as x approaches c, provided that all limits involved exist. And I said this is true. This is theorem 1.20, the difference rule.
Yes, absolutely. Excellent. Excellent. How about 1B? Jacob?
True or false, if f of x is within 0.25 units of 7, g of x is within 0.25 units of 2, then f of x plus g of x is within 0.5 units of 9. And I said that was true.
Same.
Yeah, using the
Same theorem says the same thing. Some rule instead of the difference, but the idea is the same. If we can get the output f of x values and g of x values within certain epsilon, the 0.25 is the epsilon there, then we should be able to get the sum within epsilon of its value. Good. How about C? 1C. Sydney, you want to take that one? Please.
True or false, if f of x is within 0.25 units of 7 and g of x is within 0.25 unit of 2, then f of x times g of x is within 0.5 units of 9. I said that was false because it doesn't match the product theorem.
Correct. What would make it true? I agree with you. What would make it true? If the hypothesis was true, then you want to the conclusion. Then, what one thing can you change in the conclusion to make that one true? Do you understand the question? Want to friend somebody? Good to hear you.
Wouldn't it be the same if you, like, it would be true if you changed multiplying f of x times g of x to adding f of x and g of x?
If you changed f times g to adding, that would be one change that would fix it. I agree. Excellent. Can you see another change that would, a single change that you could change in the statement that would also make it true? So that would be one of them. That's one way to do it. Yes. Josh.
Could you change the unit of 9 to the unit of 14?
Yes, that would also do it, because that would make it a product. Good, good, okay. So yeah, I agree, Sydney, it is false, and those are a couple quick fixes that could make it true. And you're right, it doesn't match the definition of the product. Okay, 1D. Sydney, could you take that one, please?
True or false, every algebraic function f is is continuous at every real number x equals c. And I said false because of theorem 1.22. This is only true if x equals c is in the function's domain.
Excellent, exactly right, good. How about 1E then? How do you take that one, please?
True or false, every power function f of x is the lowest
Yeah, because for any k value, k could be 7, k could be -3. Anything 2 for x is not a problem, but it's in the domain. 2 will always be in the domain of a power function. Now 0 is a problem sometimes, but 2 is not. You know? And the way that power function is written, 2 will always be in the domain. Okay, 1F. Please, you take that off. Mason raised his hand, but at least, go ahead.
True or false, the function f of x equals secant of x is continuous at x equals pi over 2. I said yes, because it's how it works.
What? I couldn't hear you.
I said true to that because that's how period works.
Well, trig, one of the rules I just wrote up here that's in this section is that all transcendental functions, transcendental meaning transcends the normal, so it's not algebraic. Algebraic functions have a finite number of additions and subtractions, and transcendental, it's infinite number. So that's what distinguishes them. So your trig functions are transcendental, and they are continuous at every point in their domain. The question then comes down to, is pi over 2 in the domain of secant of x? Amy, what do you say?
I put that it's false because secant is 1 over cosine, so cosine of x cannot equal 0, which it does at pi over 2.
Correct. That's correct. Cosine of pi over 2 would be 0, and that would make secant of x undefined with pi over 2, as Sam just described. Okay, G. Watch.
Yeah, he said Josh.
Okay, sorry, taking notes.
Josh, you already went. You get to go twice. You're lucky today.
Yeah, me. Okay, G. The value of x minus c of f of x over x minus c of g of x at x equals c is equal to the limit of f of x over g of x at x equals c. And I said this was false. They don't have the same domain. It would be as x approaches c, not as x equals c.
Correct. If it was the limit and not the value, you're right, because the value x equals c is not in the domain. You're absolutely right. Good. 1h. False. Okay, so you want to take 1h? Just here. Figure it out.
True or false? The limit of x minus c of f of x over x minus c g of x as x approaches c is equal to the limit of f of x over g of x as x approaches c. And I put that's true because what I imagine they did was they just canceled the common factor on the numerator and denominator.
Yes, that's exactly right, because you're not at x equals c, you're close to it. So you can cancel that common factor. In fact, that statement 1h, sorry, I'm going to come over here now. Statement 1h is what's called the cancellation theorem, which I put again this list on here. I had it up getting so that you could see that's one of the theorems that we have, along with the continuity of algebraic functions. So again, algebraic functions are things like polynomials and power functions. Anything that can be created with add, subtract, multiply, divide, and a finite number of terms. Middle functions are things like trig, exponential, logarithmic. Transcendental, as I just described, can be seen in Calc 2 as an infinite algebraic function, so that's why it transcends the finite. Anyway, they are continuous on their domains as well, so we got pretty much everything is continuous on their domains. That's nice. Cancellation theorem allows us to handle certain types of situations. And then the composition theorem allows us to handle another type of situation where we can implement it inside the function. Okay, so those are the key ones that we've seen. Besides the sum and difference and product, which I suggested that the sum and difference and product and quotient theorems kind of all rolled up into this continuity of algebraic functions. Put all that together, you get continuity of algebraic functions. Okay, what else in this section? They define for us the number E. Well, before we do that, squeeze theorem. So, what's the squeeze theorem say?
Squeeze theorem.
On page 125, to hopefully avoid having to draw this, on page 125 is called the squeeze theorem. You have a L function, L of x, is smaller than or equal to f of x, is smaller than or equal to u of x, which u is the upper function. So L is the lower, u is the upper function. If f of x is between those two, then the limit as x approaches c of f of x has to be the limit of those other two if they both equal some number L. So like the picture shows down below, and I think what we're trying to get you to see, it doesn't have to be at the origin, it can be anywhere on the graph, but if two functions have a common limit value at some c value, then if there's a third function that's between them, then it has to have the same limit value. It kind of makes sense by the picture. Y'all with us there? So as x gets close to 0 on the picture, the limit of u and L are both 0. And since f of x is between u and L, then the limit as x approaches 0 of f is also equal to 0. And so they use that theorem. It's a fairly obvious theorem. They use it on the next page to show that the limit of sine of theta as theta goes to 0 is in fact 0. They do a kind of a geometric argument. I'm going to go into this one. So I want to show that the limit theta goes to 0 of sine of theta equals 0. Maybe I should use x because my thetas look like a 0. So let's just change that for that. And they use a geometric argument there, and then the squeeze theorem. So if you think of a unit circle, this would be my angle x that I'm talking about. They were using theta. That vertical dimension, we learned in trigonometry on the unit circle. So this dimension is 1. All the way out across here is also 1. Dimension in here is sine of x. And we also know that as an angle x, if we measure it in radians, the length of this arc, the curve, is also x. So we should be able to see that sine of x, as we get close to x being 0, so an angle size of 0, we should be able to see a relationship here that as we're approaching 0 from the high side, that the angle size x is going to be bigger than sine of x. This angle measure is bigger than that side because it's curved. It's got to be longer. Shortest distance between 2 points is always a straight line, so curve's got to be longer. And we're always bigger than 0. We're approaching 0 from the high side, so we're always bigger than 0. And then we can use the squeeze theorem on this. This is now traffic function we're concerned about between two other functions. So think of this as this is the bigger function. So this is my upper, so u of x, x. Smaller function, so this would be L of x. And this function in here is my f of x. I'm just matching up what they have, except for I've got it written the other direction, but whatever. So my upper function is bigger than f of x, and that's bigger than my lower function. Now look at each of these endpoint outer functions, look at their limits. So if we look at the limit of this one, limit x goes to 0 of u of x, which is x. When x gets close to 0, what does the limit of the function x equal? One has even a stab of a guess, or are we just pretending like we don't know?
Is it x?
Oh my God. Isn't it 0?
Yeah, how do you know it's 0?
because you plug in, or you substitute c for x, and because c is 0 and the function is just x,
Yes.
it's.
And why? Absolutely, you're right. I'm sorry, I can't see this. Chloe, thank you. Which theorem did you use, Chloe, to say I can just substitute in my c value?
I don't know, it's the one with the k.
Continuity of algebraic functions. This is a linear function, mx plus b, so it's an algebraic function. Then what about over here on this side? Limit x goes to 0 of the function 0. What do you think that's going to get close to?
Okay, I'll just dump on this one.
Up on that one?
0.
This is 0.
So a function of 0, what does that function graph look like? Y equals 0.
It's 0.
This is just
Horizontal line on the x-axis, right? So if I get close to x equals 0, my y value get close to on that horizontal line.
0. Right?
You say something earlier? I heard someone say, I think. Jake, did you say?
If it's indefinite,
Nobody said it.
Indeterminate. Indeterminate.
if it's indeterminate, I'm gonna be mad.
I don't think it's indeterminate. One more time. Think of the function y equals 3. There's a function y equals 3. We all see a function y equals 3 there?
Mm-hmm.
If I say, there's the number 1, and I ask you the limit x approaches 1 of 3, what would you say that is? So as your x values get close to 1, what do your y values seem to be getting close to?
3.
Pretty close to 3. In fact, they're always 3, so it's going to be 3. So what's this one going to get close to?
0.
It's also close to 0. What we've shown is that we've squeezed the sine of x function. Sine of x function is now squeezed between a 0 on the low side and a 0 on the high side. Since it's squeezed between zeros on the low and high side, then it better have a 0 value itself. Okay, so that's the squeeze theorem, and this one quick application to show that the limit x approaches 0 of sine of x is 0. Now, they do this in the book. They do this proof using the squeeze theorem before they introduce the transcendental functions theorem. So back on this board over here, this transcendental functions theorem, continuity of transcendental functions theorem, this theorem right here would tell me the answer is 0 because the number x equals 0 is in the domain of sine of x. So I could calculate sine of 0 and determine it, but they were doing the squeeze theorem before they introduced that transcendental. So they have the continuity of exponential logarithmic. Before they do that, though, they introduce the number e. So I guess. How do they define that? Have you seen that kind of definition of the number e before? You're familiar with the number e in pre-calculus, right? That's. Have you seen that definition of the number e before, anyone?
Is he asking?
Have we seen that definition of e before?
This particular one?
Yes.
How have you seen it defined previously? How was e defined previously? Or was it just kind of stated, here's e? Basically, here's E. Who's it? Here we're finding what E is from a limit standpoint. One of your homework exercises is actually to make a table of values as H gets close to 0 and see that you get E. So that's easy. Then we get a theorem about it that we can use for some other things later. Limit x goes to 0 of e to the x minus 1 over x.
Oh, gosh.
Is what? Theorem says it's 1, doesn't it? But do you notice that this is going to be indeterminate if you, quote, plug 0 in?
Yeah. Dang.
So e to the 0 is
1.
1. And 1 minus 1 makes 0. And then you got a 0 on the bottom. So this is indeterminate 0 over 0, but the theorem says that it's 1. So initially, it's 0 over 0 indeterminate. But the theorem says it's 1. We can kind of roughly show that from up here, the definition. We can kind of loosely show this. From the definition, we can say that at h close, whatever that means, to 0, we get E is approximately equal to 1 plus h to the 1 over h. So we're saying that E is defined by this limit. I'm saying, well, if h is very close to 0, then I can say it's approximately equal. It's definitely equal when we do the full limit, but it's approximately equal if I'm close. And from there, I can just do a little bit of algebra. So you can raise both sides to an h power. So you get e to the h equals 1 plus h. And then you can subtract 1 from both sides. So you get e to the h minus 1 equals h. And then you can divide both sides by h and get e to the h minus 1 over h equals 1. Well, technically, these are all approximate. Since I'm all very close to 0, then this statement and that statement look alike, and I can say roughly besides that. Okay, so those are some things about E in this section. Continuity of trigonometric functions we already mentioned. So now we have homework exercises. Did you have a chance to try any in section 1.5? We've now covered all of the material in 1.5 line. We've covered the theorems about continuity. We've covered the definition of E. Haven't done any examples with this or anything, but it's not too bad, I don't think. So any questions on the homework that you were supposed to work on? 53. Okay, let's talk about 53. I'll go here in the middle board. 53, what does it have?
Limit 2x over x minus 1 x expression 0.
Okay, good. So I'm going to do this in a way that I would, expect to see, like on a test, coming up. I'm going to apply some of the properties we've learned just to get this in a form that I can evaluate. The first property I'm going to recognize is that there's a 2 multiplier in here. And one of the first properties we saw was a multiple. If you have a constant multiple times anything, you can pull that constant multiplier on the limit. Remember that very first term? Turn on your page 123, theorem 1.20, very first row says constant multiple theorem. This limit k is supposed to see if k times f of x is equal to k times the limit of f of x that's supposed to. So you can, if you have a k inside the limit that's a multiplier, then we can pull that k out. So I can just write this as 2 times limit why can I do that? That was the multiple term. Okay, I'm getting closer to something I can work with. This looks strangely like or similar to the theorem we just discussed on the other board. You with us? So very similar to that theorem over there. It's not identical, so I'm going to rewrite it. So I rewrote it as a reciprocal of the original raised to a -1 power. Do you all agree algebraically that those two are equivalent? Mm-hmm. I just did algebra. No calculus involved there. So that's just a property of exponents. Why would I do that?
Because it looks familiar.
It's very familiar. And I have the composition theorem over here on the first board again. Composition theorem says that if you have the limit of a function, you can do the function of the limit. So I'm seeing this as a outside function is -1 power. That's my f over there. Inside function is e to the x minus 1 over x. So I can rewrite this as, by the composition theorem,
oh gosh. My body was not ready.
make sure you're clear on that. The -1 power, which is all it's doing is causing reciprocal, I've moved it outside of a limit by the composition theorem. How we're basically done. What is the limit as x approaches 0 of e to the x minus 1 over x? By theorem, it is 1. 1 raised to the -1 by the, they give a name to that theorem? I think they call it another view of E or something. I don't know. Let's call it the E theorem. So that's 2 divided by 1, which is 2. Does that answer your question, Jacob? Anybody else follow that as well? Okay. Any other question you want to go over? Got several on the other. Razor, what's your question?
So now we do 41.
41. We do 41. I can try to do 41. Read it to me, Razor, please.
Read it to you.
Okay, it says the limit of x minus 1 over the root of x minus 1 as x approaches 1 from the right.
Okay, so if we attempt a continuity of algebraic functions, because this is algebraic, try that rule, quickly run into a problem of indeterminate because 1 is not in the domain.
Yeah.
So this is 0 over 0 indeterminate. So I can't actually directly apply the continuity theorem because it's not in the domain. But it's just telling me that I've got this something going on I need to work with. Just like over here, let me make a mention to you. Back over here, I should have mentioned this at the beginning, I apologize. On this first one, take an observation on this number 53. If you had tried to do the continuity of transcendental functions, because e to the x is transcendental, and x is algebraic, so I got algebraic and transcendental both in there. If you had tried to apply the theorems to it, this one would have come out to be 0 over 0 indeterminate as well. So I knew I had to do something different, and so I started working. My thought process was, well, I need to get it to something I can work with, and I matched it up to a theorem. Over here, I've still got the same kind of starting point. I've got this 0. If I plug in 1, I get 0 and 0. So what can I do algebraically to manipulate it so I can get it to work?
What can you do? Oh my. Oh my. That's clever.
So x minus 1 is the square of the square root of x minus 1. That's clever, you're right, a little trick about them.
I wish I was that creative.
And so we have seen by the cancellation theorem that as long as I'm not at the value that's causing the indeterminacy, and I'm not because I'm doing a limit, I'm getting close, but I'm not exactly at it, then I can cancel a common factor out of these. So this is the limit. X approaches 1 from the right of the square root of x minus 1. So let's see, what did I do here? This is a property of x1 skin. And this is a cancellation theorem. Excuse me. As long as we're approaching 1 from the right, meaning you're bigger than 1, and you take the square root of it. Go with me. What if you were approaching 1 from the left? Would this be workable?
No.
No, you get an imaginary number because you'd be on the left side of 1, which would make this inside be negative. As long as I'm approaching 1 from the right, then I'm always bigger than 1. So something bigger than 1 minus 1 is always positive. So I can take the square root, and it's getting very close to the square root of 0, which is 0. And this would be the continuity of algebraic functions. Make sense now, Rezo?
Yes.
Anyone else follow that as well? Okay, time for another question, maybe. $59. 59, honestly, tricky only because you think it's going to be indeterminate, but it's not.
Lost me.
So, drawing out my continuity of algebraic and or transcendental functions, an inverse trig is a transcendental function. And it's multiplied by x, which is an algebraic function. So, as long as the C value is in the domain, I can simply plug in to effectively give me the limit value. Is 1 in the domain of x? This x right here? 1 in this domain?
Yeah.
The domain of both, so I can simply evaluate by plugging in by the continuity theorems.
Yeah.
So this is equal to 1 times inverse sine of half by the continuity of algebraic and transcendental functions. Whatever that number is. What is inverse sine of half?
Pi over 6.
Yes.
Wait a second. Why is that?
No.
Oh my god.
What was that? I'm sorry.
I'm used to it being written pi over 6.
Crazy though. That's fine. My little brain kind of thinks of it differently. I think if pi is halfway around the circle, then half of that would be a quarter of the way around the circle. So to me, I don't think of pi over 2. I think of it as half of pi. And so 1/6 of pi is.
Oh my gosh. That's not cool. Why wasn't I told this? I couldn't think of things spatially. I was just forced to memorize it.
You were forced to memorize it. See, I'm not big on that. I like to think of, so instead of 3 pi over, so think about 3 pi over 2. 3 pi over 2, I'm like, what does that even mean? But think of it as 3/2 of pi. That's 1.5 of pi, right? So that's 1 pi plus a half more. It makes much more sense to me than 3 pi over 2. I'm not sure why I get started one way and not the other. I retire and have lots of extra time. I'm gonna write my own pre-calculus book, and that's how we're gonna always write on. I'll handle it either way, Ray. So if you want to write it as pi over 6, that'll be fine by me. That's not
I'm just pretty much.
Yes, Dylan? No, Josh, I'm sorry. Josh.
Number 57. I don't
Yeah.
know, read it.
You're gonna read it, Katie?
Well, like the symbol, I guess. Could you read it to me, please?
I would love to. Okay. What is? I don't know. What limitation of sine of x over tangent of x as x approaches 0. Yeah. What does that equal?
Okay. So once again, if I try my continuity theorems, I've got transcendental in here. So if I attempt those theorems, what happens? So if you plug in a 0 for sine of x to come close to the limit, you find that that's 0. And if you plug in a 0 for tangent of x to see what the limit value might be, then tangent of 0 is also 0. Permanent.
We've reached an impasse.
So we need to find something else we can do than simply the continuity theorems. when I can apply the continuity theorems, I'm going to use them because those are easy. Just let me plug in to effectively evaluate the limit. Otherwise, I got to do some more work. So what can I do?
You can transform the tangent.
Yes. Using an identity from trig, I can get this. Oh, wait, what?
Not the taxes.
The tangent is not equal to sine over tangent. That doesn't make any sense. Hold on once. What does that give me?
They're all zero.
No, it doesn't do that. It's just like a circular loaf of bread. And a Yiddish origin.
How can I get it to 1 over cosine of x? What theorem have I used to do this right here?
Cancellation. Yeah, cancellation.
Yes.
Dang. Got him.
Okay, and then by a little algebra trickery, this is just cosine of x.
Yo, hang on a second.
And when x gets close to 0, cosine of x gets close to
1.
by the continuity of transcendental functions. Yes. 0 is in the domain of cosine, so I can plug in to figure out approximately what I think the limit is. I'll get 47.
What about 47?
It's between 46 and 48.
Yeah, what about it?
And when you go silent for 30 seconds.
Well, he's really thinking about it.
He's writing it down.
He's in the middle of it.
Maybe they're all actually drowned.
They're all actually drowning in isothermal.
You're right.
Please, I'm sorry, what now? Everyone give me 1 second.
We can't see
I can't see.
anything.
What
I
can you
can't
not
read.
see?
You just have the last problem that we did.
Have you started anything else, or?
I mean, we did 57 was the last one I did, and I asked you about number 47.
Oh, okay.
Well, what about 47?
Yeah, just.
Okay.
What about it?
How do you get the answer? What's the answer, and how do you get it?
Well, 0 divided by 1 is 0.
Yes. Whereas 1 divided by 0 is not 0.
Yeah.
Okay, good. Any other questions on this homework? What about the piecewise defined functions? Did y'all figure out the types of discontinuities there? Would you like 71 through 77?
You think you could cover one of those?
Cover one of those. Is that like a cover band or something?
What did he say? Did he say Cobain? Melbain?
I said cover band or something.
Cover band? What's a cover band?
And these covered bands are popular right now.
Like those? Wow.
So let's
Like,
see.
this is what I live for. The isothermal cover band.
Don't knock it, you try it now.
gotta draw something now.
We're gonna end the class next period.
Yeah.
We're just gonna stop the discussion.
Okay, so just find, I just made up one so you can, if you haven't tried the ones, the books, you can still have an opportunity to try your own now. The directions would be find, meaning locate, meaning what X values do we have discontinuities, identify the type of discontinuity, and look at left and right side continuities. So, you see anything that looks suspicious there that you might look for a discontinuity? Jacob held up the inside curveball to me. Okay, yes, two might be suspicious. Anything else that might be suspicious for you?
Straight
Suspicious. Anything else that looks suspicious to you? What about X equals 4? Why might that be also suspicious? Why am I suspicious about X equals 4?
Why? I don't see no 4 there. But I mean, I see the 4, but not in the function. But I see it elsewhere.
Okay, so why did you decide that X equals 2 was suspicious, Jacob? Because it causes some kind of something to happen in the function. And likely going to be an aspect or something. What about X equals 4? What makes me think it might be suspicious? Might cause some kind of hairy problem. I changed function rules at 4. So I could have a jump. Don't see this now? So we'll examine that.
What's a jump?
At X equals 2, what do we have?
A plus
Well, when X approaches 2 on the left, of f of X, if I'm approaching 2 from the left, what's happening with this function? Well, I'm using this function rule. Now let's discuss. When X gets close to 2 from the left, what is happening to the numerator of this? If I apply my quotient rule, what's happening here? Am I getting close? Quotient rule allows me to do the top and the bottom separate. Look at the X minus 1. Just the X minus 1. As X gets close to 2 from the left, we're approaching 2 from the left. This is approaching what? 1. This is getting close to 1 on the left. Do we agree with that?
Mm-hmm.
Smaller than 2, always smaller than 2, and so you're always going to be smaller than 1. What about the denominator? As X approaches 2 from the left, what's happening to the denominator? approaches 0 from the which side?
From the left.
Correct.
I'm
Now, before we finish the answer, listen up. Will it always be from the left just because I had a left on here? Because I asked the question, probably not.
Probably not.
If it had been 2 minus x instead of x minus 2, see, it's going to change your sidedness. Why does the sidedness matter? What does that give me? Well, if I have a number pretty close to 1, like let's say 0.99999, and I divide that by a number that's pretty close to 0 on the left side, give me an example of a number close to 0 but on the left side.
1.
Negative 0.00001, Joe said. That's right, Joe. So now take out your calculator and divide 0.99999 by negative 0.00001. What do you think you're going to do? Really big negative number, Joe said. That's right. So as you get closer and closer to 0 as a divisor, the overall fraction is going to get bigger and bigger and bigger. And because you're dividing by a negative, then this can actually go to negative infinity.
Are you telling
Oh,
me
that
there's
thing.
some toad where it can't be horizontal? That's crazy.
Yeah, we're not talking about horizontal asymptotes here yet. We're just finding the vertical asymptotes. Tell us approach, limit x approaches 2 from the right.
Oh, yeah. The right is always right.
Words to live
If I approach 2 from the right, what happens this time? One from the right, and you approach 0 from the right, which gives me positive infinity.
Oh, my. I was not ready. I can't believe my eyes.
What would you say about the limit as x approaches 2 in general? If I asked that question.
Could you say, I don't know, it does not exist?
Correct, does not exist. If both of these had been positive infinity or if they've both been negative infinity, then you could have put that down as your answer. But what kind of discontinuity is this now?
Infinite discontinuity.
Right, that was tried for infinite discontinuity.
I was a fool.
Okay, now what was our other suspicious point? X equals 4. We need to examine what's going on in x equals 4 as well. Oh. Guess what? Same game, folks. I need to understand what's happening at x equals 4. So I got to look from the left, I got to look from the right, I got to see if they match up, so on. Okay, so limit x approaches 4 from the left of f of x. It's going to be the limit x approaches 4 from the left. Which rule am I using when I'm approaching 4 from the left? First rule. How did you know that, Jacob?
You use numbers last.
So, yes, I'm approaching 4 from the left, and I'm smaller than 4, which puts me in the first rule. Now I use my continuity of algebraic functions. This becomes 3 from the left, and this becomes 2 from the left, which is You might need to pan over just a little bit. Okay, so now let's try limit x approaches 4 from the right. F of x. Now we're bigger than 4, so I'm going to have to use this rule. My continuity theorem for algebraic functions, I get
Is that 17? Is it 17?
that's 16 plus 1, which is 17. Okay, so both those were by the continuity theorems. Continuity.
More like a discontinuity.
What does this tell me now?
Is that a?
It doesn't make sense.
Yeah, it doesn't exist.
Limit x approaches 4 in general does not exist. Good. And what kind of discontinuity do we have?
It's a leap or a jump.
That's correct. Okay. That's the kind of thing you got to be able to do. Is examine the left and right limits. Oh, on the left and right, let's go back one more time. At x equals 2, is it left or right continuous? No, but at 4 it is left continuous because f of 4 is 3/2. So it's a jump discontinuity, but because f of 4, if I just evaluate 4 in this function, I'm going to use the first rule, so that's 3/2. This means we have left side continuity. I've got two different things going on. At x equals 2, you had an asymptote. That's one type of thing. On this one, we have a jump discontinuity. That's a different kind of thing. And we can talk about at a jump whether we have left side or right side continuity. We have left side continuity because F4 is equal to 3/2. All right, so I think we're almost out of time. We got like 2 minutes. What about the later problems like 63, 65? Did y'all figure out what to do with those? I figured out number 63 or 65. They're very similar. Notice it has a suggestion set. You getting help on internet?
Just for
Well, for example, on 63, what I would suggest for everyone, if you quote on 63, just look at number 63 for a minute. Try in your mind to just plug in 0 using the continuity theorem. So if you plug in 0 for h on 63 using the continuity theorem, what happens? In indeterminate form, right? You get 3 plus 0, which is 3, squared minus 3 squared, which is 0. And the denominators, you get 0 over 0. So my suggestion then is you need to do something to try to cancel. So what I would suggest is distribute everything out so that you can factor it, simplify and factor, and you should be able to factor like cancellation term back over here. If you can get a factor of the same thing in the top and the bottom, you can cancel it and get down to here. Well, what's in the bottom? What's the only factor in the bottom? H. So I need to find the H factor in the numerator and cancel it, and then my indeterminacy is gone. That makes sense? So you need to distribute out, factor it, you combine like terms and factor it, and hopefully you can factor an H so that it will cancel.
Was it want me to do FOIL? Oh my gosh.
It's not too bad once you do that. Another way to handle it instead of distributing out, look at the numerator of that number 63, real quick. Again. What then you could do is you could square out that 3 plus H. We just said that.
Square up.
Well, properly, you can distribute the product of those two binomials. But another way to handle it is, you see, another look, thinking differently, instead of distributing and then combining like terms, is there something else you could do that might shorten your work?
Got him.
I'm focusing on the numerator. My objective is to get an H factored out. I could either distribute out and combine like terms and then try to factor, or maybe I can factor right now. If you're paying attention.
Oh crap. How?
A difference of 2 squared.
Oh no.
Well, it factors as is. So this would be 3 plus H plus 3. 3 plus H minus 3.
Dang.
3's here cancel, leave me an H factor. That cancels with the bottom H factor, and we're almost done. Okay? Well, for tonight, finish up that homework. Read section 1.6 so we can get going on it tomorrow. And try problem 1 of section 1.6. So homework, finish 1.5, read 1.6, try problem 1 of section 1.6.
I never understood my laugh until today. It's all opened up. The clouds just rolled back. Duty, the isothermal cover band. Yeah. Album 1, Gattaca.
I heard it. Oh, you did find one.
The second one,
You're tired? You got it fixed? So it hold there or not really? You have enough air to get to here, and now you gotta find a compressor again.
Right. I think that.
So you say something bigger than one here and less than one here?
right?
Yeah, so like
But I
let's
did
say
not know
you do
what the
0.9999 divided by
That might have just been a basic
-0.001.
miscalculation.
You get a giant negative one.
That makes sense.
Yeah.
These?
You can just plug it in and then.
Okay, closer. Thank you.
Okay, so what I was
Jim?
getting
Once again, we still haven't got
No, I don't know. He just needs to have a stronger immune system.
Really, he does.
I have all this global.
I mean, the idea is
Oh,
that you
yeah.
put
A lot of.
you end up with
And if I should plug in the actual value of
Okay,
E,
right
I
now.
talked to Lee
That was the
Smith,
fair.
pictures,
like whatever one I get
on
book,
some of her contacts.
that was what I was getting each of these
Oh, no,
like
no,
in
no.
falls.
So you would just literally type in the first -1 over 1.
You're actually not looking bad today, isn't it? I'm proud of you.
I would pay to see this
We look at Stacy today.
Wait, what type of genre do you think they would classify?
Yeah, classic rock.
Probably a lot of